Chemistry Kinetics with Eli Tautab and Zach Zane. Today, to start our discussion, we will be talking about determining reaction order and figuring out what reaction order is. Now this is an interesting question. Let's ask our book, Brown and LeMay, what reaction order is. We see here that reaction order is the power to which the concentration of a reaction is raised in a rate law. You may be wondering, what is a rate law? Well, here we have it. This is what we call a rate law. And when we determine reaction order, we're trying to find the powers that these concentrations will be in the rate law. Here's Eli to talk a little bit about determining that.
So when we're trying to determine the powers on our initial concentration of reactants in the rate law, we're going to go to a chart like this. What we're going to plot is the initial concentration of each of the reactants versus the initial reaction rate. So we'll start with a known of 1A and 1B to start, and we see that the initial reaction rate is 10. And then what we're going to do is we're going to change the concentration of one of the reactants. So in the first example, we'll double the initial concentration of A and see that the initial reaction rate does not change. This signifies a 0th order reaction. And in the second example, we will bring A back to 1 and double the concentration of B, and we can see that as B doubles, the initial reaction rate also doubles. That is a first order reaction. Alright, so for our second example, we're going to go over a little bit more of a complicated reaction order problem.
Here you can see that we now have reactant C, reactants D, where before we had reactants A and B. So like Eli said, it's going to be a little more complicated. We start with our initial concentrations and our initial reaction rate over here, 3, 2, and 10. And we can compare these others in relationship to that. As we see, reactant C goes from 3 to 9. That, of course, is tripled. What being tripled will change our initial reaction rate by 9 times. And of course, that is squared. So thereby, the reaction order is 2. We can now analyze and continue based on the concentration of C for the second trial in our new reaction rate. We have 9 to 90, we can go from there. Our 2, as our 9 changes, stays the same, goes up by 2 times, that's a 4, which relates to this reaction rate, 90 to 80, being also 2, and thereby the reaction order is 1. Alright, now we must talk about what is the rate constant and how it can be determined using graphs and graph extrapolation.
Alright, so we're going to start with the 0th order reaction, and this, if you remember, is when the initial concentration of A does not affect the rate of reaction. So we can see as the concentration of A decreases, the slope of this graph is not changing, and that means that the concentration of A does not affect the reaction rate.
Then we continue. If you remember, we have our first order and second order reactions, and these are a little bit more complicated finding the derivations of, but experimentally we have found that in the second order reaction we have 1 over the concentration of A, and in a first order reaction we have the natural log of A. And so when you have data and you're trying to determine what your reaction is, you're going to go ahead and plug into different functions and find which one provides you with the most linear slope, which is also your K from your rate law. And whichever one gives you the most linear slope is the reaction that you have. Again, this is first order, natural log, and the second order is 1 over A. Rate determining steps. That's easy. Eli?
So for rate determining steps, what we're looking at is which of the steps in a multi-part equation is going to be the one that determines the rate. So as you can see, we've got 3 parts to an equation here. You've got a fast, a slow, and a fastest section. So just by logic, you would say the slow step is going to be the one that determines the rate. So a good visualization for this is as if these reactions are in a race against each other, going from the start to the finish line. You can see the fast step is about halfway there, the fastest step has already completed, but for the reaction to be completed, the second step has to make it all the way to the end. So that, in a nutshell, is the rate determining step right here.
What about rate laws?
Oh, integrated rate laws. How to.
All
How to
right.
get that to work.
Here we have our rate law equation from earlier. You guys probably remember this, where our rate equals our, right here, K times concentration of A. And this is actually what we call a differential equation. You can see our dA dt, we can turn this change in concentration we have here, our rate, into a calculus function here, dA equal to dt, where A is for concentration. And then we can plug those parts together and we get this equation right here. And so if we want to direct, well, a rate law, an integrated rate law, if we want to direct comparison to concentration and time, to link those directly like that, we're going to go ahead and integrate using calculus. And so we come right down here, combine your variables, this equation up here, get your a's together, and then your t over here with this k. Of course, you have our negative from right there, and then you're going to integrate from, you'll start from A to your new concentration that you want, and then you'll go from 0 to T, plug that in, and then this is your almost final product. You'll take this and you can simplify it to a couple alternate forms. This one at the top right here, obviously that's just adding this natural log function to this side. This one's kind of nice because it kind of gives you an mx plus b layout, and then you also have this one right here. If you e both sides and then drop that natural log out. Methods of monitoring rate of reaction.
Alright, so in previous sections, we have been given initial concentrations and initial rates of reaction in order to figure out our orders of reaction and rate laws. So in this section, what we're going to do is we're going to figure out different ways that we can actually experimentally determine the rates of reaction. So our first one is the colorimeter. This plots light absorbance versus time. So it's useful for, in cases that you have appearance or disappearance of colored ions, you can track how much absorbance there is over time. Next is the pH meter. And this is useful for when you're doing acid-base chemistry. It plots the concentration of hydronium and hydroxide ions over time. So as acids and bases are mixing and those two ions are appearing and disappearing, we can track their concentrations. And lastly, we have visual cues and measurements. This is a pretty blanket term for a lot of different things. We have just watching how fast a precipitate is forming, change in color of a solution without using the colorimeter, bubbling, and in some cases, like the one that we may be demonstrating later, burn rate. So these things are mainly qualitative. You're not going to get a lot of good data off of them as opposed to the colorimeter and pH meter, but they're still useful for determining how fast reactions proceed. So our final section is going to be on catalysts and their effects on rate of reaction.
Okay, so catalysts are quite the interesting thing. They can have, like Eli said, an effect on the rate of reaction, but they don't actually participate in the reaction. So how catalysts actually work is they lower the activation energy, and we can see this on this nice little graph that Eli has drawn for us here. This top peak here is the activation energy in a reaction that has not had a catalyst added to it, and then the lower one here in purple is the reaction that has had a catalyst added to it, and of course you can see the reaction activation energy is a little bit lower, and thereby the reaction will be a little bit quicker, and you can see this right down here. The purple is down at your final endpoint a little bit faster.
It's time for the moment you've been waiting for. Da 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 da
and I need you, and I miss you, and now I wonder if I could fall into the sky. Do you think time went past me by? 'Cause you know I'd walk 1,000 miles if I can just see you tonight.